All right, welcome back. Today we're jumping into something really cool, local search algorithms. Basically, we're going to talk about how to teach a computer to solve a super complex problem by finding the absolute best solution, not just, a pretty good one.
But that brings us to the real puzzle, right? I mean, it's easy to find a solution that's good enough and then just stop. So the big question is, how do we build an algorithm that doesn't get tricked? How do we make it smart enough to ignore the good enough options and keep searching for the best possible one?
And this is the trap we're talking about. It's called the local optimum. Just think of this picture as a map of every possible solution. A simple or greedy algorithm is like a hiker who can only walk uphill. So what happens? They start climbing, hit the top of the very first hill they find, and then they're stuck. Every direction from there is downhill. They have no idea that the real highest peak, the global optimum, is just across the valley.
So here's what we're going to cover. We'll start with why we get stuck in the first place. Then we'll look at our first solution, something called simulated annealing, and break down how it works. After that, we'll check out another approach, local beam search. And finally, we'll put them side by side in our optimizer's toolkit. Let's get started.
Okay, so let's quickly nail down this getting stuck problem. The reason a simple greedy approach fails is pretty straightforward. It's fast, sure, but it's short-sighted. It only ever takes a step that gives it an immediate improvement. Once it hits a peak, any peak, it can't go any higher, so it just stops. It has no way of knowing if it's on a tiny little foothill or the summit of Everest, and that's exactly why we need these more clever strategies.
All right, on to our first solution. This one's called simulated annealing, and honestly, it is such a cool idea. It's actually inspired by a real-world process from metallurgy, working with metals. It's a perfect example of how we can borrow ideas from nature to solve complex computer science problems.
So in the real world, when a blacksmith is working with metal, they use a process called annealing. They heat the metal way up, super hot, and then they cool it down, but really, really slowly. Why? Well, this gives all the atoms inside the metal a chance to jiggle around and find the perfect arrangement, settling into a super strong, stable crystal structure. And believe it or not, that physical process is exactly what we're going to copy for our algorithm.
So let's walk through it. Step 1, you heat the metal up, a lot. This gives the atoms inside a ton of energy and they start flying around almost randomly. Step 2, you start to cool it down, but you do it gradually, following a very specific schedule. As the temperature drops, the atoms start to calm down and settle into place, finding that perfect, low-energy structure. Makes sense, right?
Okay, so how do we turn this into code? Well, we do the exact same thing. We start with a high temperature, which is just a number in our program that represents randomness. When the temperature is high, the algorithm is allowed to make bad moves. Think about that for a second. It's allowed to move downhill sometimes. And that's the absolute P. That's what lets it escape those little local peaks. Then, just like the metal, we slowly lower the temperature. As it gets colder, the algorithm gets pickier. It stops making as many bad moves and starts acting more greedy, always trying to go uphill. Finally, when the system is cold, it settles on the best solution it managed to find.
So let's get into the nitty-gritty. How does this actually work? Well, it really boils down to two things: temperature and probability. These are the two levers the algorithm pulls to make its decisions. Okay, take a look at this flowchart. It really lays out the logic. We start with some random solution. Then we look at a nearby one. Now here's the crucial part. If the new solution is better, great, we take it, no questions asked. But what if it's worse? This is where the magic happens. We don't just throw it away. Instead, we calculate a probability, and based on that probability, we might still take the worst move. This is our escape hatch from local optima. Then we just lower the temperature a tiny bit and do it all over again.
Now, this whole process is controlled by something called the cooling schedule, and this is super important. Think of it like a set of dials you have to tune for your specific problem. You need to decide, how hot do you start, how fast do you cool things down, and how long do you search at each temperature level? Getting this schedule right is honestly half the battle in making the algorithm work well.
So you're probably wondering, how does it actually decide whether to take one of these bad moves? Is it just random? Well, not quite. It all comes down to a clever probability calculation. This little formula is really the brains of the whole operation.
And here's the intuition behind it. The chance of taking a bad move depends on two things: how high the temperature is and just how bad the move actually is. So look on the left. If a downhill move is really steep, we're probably leaving a pretty good spot, so we're less likely to take that step. But on the right, the slope is really gentle.
That suggests we're in a kind of boring, flat area. So in that case, we're more likely to take the bad move just to shake things up and see if we can find a more interesting part of the map. All right, so that was simulated annealing. Think of it like a single lone hiker exploring the mountains with a bit of randomness. Now let's look at a totally different philosophy. What if instead of one hiker, we sent out a whole search party? That's the idea behind our second solution, local beam search.
So here's how it works. Instead of tracking just one solution, local beam search keeps track of k different solutions at the same time. This k is just a number you pick. Maybe it's 4, maybe it's 10. You can think of these k solutions as your beam or your search party. At each step, you look at every member of your search party and find all of their possible next moves. Then you throw all those potential moves into one big pool, and from that pool you pick the best k to become your new search party for the next round.
Yeah, I know. That can sound a little abstract. So let's do what we always do and walk through an example step by step. Let's see how this beam of solutions actually moves and evolves. Okay, check this out. Let's say our beam width, our k, is 4. We start with 4 random states. Their values are 8, 8, 7, and 6. Now, for each of those 4 states, we generate their successors, or their neighbors. So we get a whole bunch of new states. The crucial part is next. We take all of those successors and throw them into one big pile. Then, we look at that whole pile and pick the best 4 overall. In this case, that's 3 9s and an 8, and that becomes our new beam for the next step. Notice we're not just picking the best child of each parent, we're picking the best children from the entire generation.
All right, let's use a more concrete example. The classic traveling salesman problem. The goal, as you probably know, is to find the shortest possible route to visit every city once. We're going to set our beam width, k, to 2. So we start with 2 totally random incomplete tours. These 2 routes are our initial search party.
Okay, step 1. We take our first tour on the left and figure out all the possible next cities the salesman could visit. We do the exact same thing for the second tour on the right. So now we've got this whole pool of potential next moves coming from both of our starting points. Now, for the most important step, selection. We look at that entire pool of next step options we just generated. We calculate the total length for each one. And since we want the shortest tour, we pick the 2 routes with the lowest total length. Those 2 winners, highlighted right here, become our brand new beam. They're our new search party. And from there, the process just repeats. These 2 new tours are our new starting point. We generate their successors, pull them all together, pick the best 2, and so on. We keep doing this iteration after iteration until we have a complete and hopefully optimal tour. Okay, so we've looked at 2 really powerful, but also really different ways to tackle that getting stuck problem. Let's wrap up by putting them side by side, so you can think of them as 2 different tools in your optimization toolkit.
Let's compare them head to head. The core idea for simulated annealing is all about that random, probabilistic exploration. For local beam search, it's about searching in parallel with a team. Memory-wise, annealing is super light. It only needs to remember 1 state. Beam search needs to store k states, so it's a bit heavier. Now for the key strengths. Simulated annealing's biggest plus is that it can theoretically escape any local optimum. Its weakness? It can be painfully slow to get there. Local beam search, on the other hand, is usually great at finding pretty good solutions really fast. Its main weakness, though, is that the whole team can get stuck on the same hill, losing the diversity that makes it so powerful. And really, this brings us to the big takeaway. The art of this isn't always about finding the single best answer in the universe. It's about finding a great answer in a reasonable amount of time. And knowing which tool to pick for the job, whether it's the slow and steady explorer or the fast-moving team, is what really matters. Thanks for tuning in.